Let me start by thanking Professor Andrew Farmery for joining us today. Andrew is going to talk about the inspired sine wave test in mechanical ventilation. Andrew is from Oxford, and Andrew, I'll let you take over and introduce yourself. We have quite a nice group today, and I'll ask everyone to send me their bylines and I'll put them up. But Andrew, please take it away.
Thank you very much. I hope I'm sharing my screen now. Is that right?
You are, and now we just need it. Before you go, Andrew, I'll do it at the end. Never mind. Sorry.
Okay. Well, thank you very much, Steve, for inviting me to speak to the group. I'm Andrew Farmery. I'm a professor of anaesthetics in Oxford and head of the University Anaesthetics department, and I'm a fellow and the dean of Wadham College in Oxford. This is where I have the great privilege to live and work, and it's a very beautiful place, a medieval university seen from the sky there, lots of different colleges all kind of working independently. The college that I am a fellow of is over on the left-hand side. It's called Wadham College, and here it is. And the bay window above the gatehouse door is my room, is my college room. And I say to people that throughout the history of this college, I am the least illustrious occupant of that room, and many great people before me have lived in that room. Probably the greatest of them was this fellow here, John Wilkins, who was the warden of the college in the early 1600s and was a great natural philosopher. He was the guy who assembled around him a group of natural philosophers whose mission was to study the natural world. Up until then in Oxford, you studied theology and mathematics and astronomy and classics and Latin and Greek, and you became a priest and a bishop. In fact, this guy, John Wilkins, did, but he decided that this was the revolution of scientific thinking, and he gathered around him this group of people, the Philosophical Club. Great names here: Christopher Wren, Robert Hooke, as in Hooke's law, elasticity and stress and strain, which we'll hear a bit about later. That's him. Robert Boyle, as in Boyle's law, gas laws. Lower and Thomas Willis, as in Circle of Willis, and Mayo and Seth Warden. All these people would gather in that room. They later became the Royal Society, and planned all sorts of crazy experiments, physical and biological. And one of the experiments they performed was written up here in Hooke's folio, a lab book, trying to work out what the lungs did. You might imagine that people knew what the lungs did in the early 1600s, but no, apparently not. The prevailing thought was that the lungs were some kind of bellows that propelled the blood around the body, and the tidal movement of the lung, the purpose was to push it around the body. And so they devised an experiment with a dog, an intubated dog with an open chest, into which they formed multiple bronchopleural fistulae, and they ventilated it with a constant stream of gas going down the tube. And so the lungs were just held static, but being ventilated, of course, because gas was bubbling out of the fistulae. So the lung was still, but the dog was being ventilated. And they proved that the function of the lung was gas exchange. It wasn't a motive force. And it's written here in Hooke's folio: bare motion of the lungs contributes nothing to the life of the animal, he being found to survive as well when they were not moved as when they were. So there. And went on further to note that noting the scarlet color of arterial blood is due to the penetration of particles of air into the blood. Revolutionary. It is the nitrous spirit of air that normally enters the blood in the lungs. Of course, oxygen wouldn't have been discovered for another 200 years. So we've got to give him some leeway there for imagining it was something called nitrous spirit of air. But these were the great grandfathers of empirical science, and they were sitting in my room doing it. Quite extraordinary. Anyway, I won't to waffle on too much about that because Steve has told me I'm going to be talking about lung homogeneity and effective lung volume in mechanically ventilated patients with specific reference to villi. Now, I'm going to go through just very briefly what we have known chronologically, possibly, about what the forces are which cause villi. I don't want to go into great detail because you're experts and you're probably more expert than me, but I just want to set it in some sort of timeline so that we can criticize it a bit later. This idea of volutrauma, the idea that excessive strain, we inflate the balloon excessively, and somehow this is responsible for the inflammatory changes which underlie villi. That's been around for a very long time. The thing that's a little bit inconsistent about it, of course, is that we can ventilate, and we all do ventilate, healthy people with inadvisedly large tidal volumes and all the wrong things, and they don't seem to come to any harm. And if you're a marathon runner or a mountain runner, you yourself will breathe with enormous tidal volumes and respiratory rates and transpulmonary pressures, and you don't come to any harm. So there are some inconsistencies with that, but we grew up with this notion that excessive volume was injurious through the application of stress and strain, particularly on the lung. Hooke's idea of strain. This later idea, possibly, that's probably, I don't know, 30 years old now, but the idea of atelecta trauma, the notion possibly that the tidal collapse and re-expansion of terminal airways and alveoli generated shear forces that was responsible for inflammatory changes that might drive villi. Well, that's an attractive idea. Again, there's some uneasiness with this hypothesis because we, in my lab, have shown that actually in experimental animal models of ARDS and villi, we don't always see it, and we don't see it to a very great degree. So this notion of tidal recruitment and collapse may not be as great as we imagine. And the other uncomfortable evidential part of the idea of atelectasis comes from people like Brian Kavanagh and Goran Hedensteiner's group here. This is, and there are a number of papers here, but this is one that's fairly well known. Atelectasis generates inflammation and structural alveolar injury in the surrounding healthy tissue in mechanical ventilation. So it's not in the atelectatic tissue where the injury occurs. It's actually in the distant, albeit surrounding, healthy tissue. So this doesn't quite fit with this sort of notion of shear stress from collapse and re-expansion. So there are some inconsistencies in the hypotheses and the evidence here. And the third thing, just moving slightly chronologically through this, is this more recent understanding that the power that we dissipate within the lung, whether we're doing it spontaneously or more likely that we're being mechanically ventilated, the mechanical power dissipated in the lung tissue is the stressor or the injurious thing. And there are lots of versions of this equation, but not surprisingly, it's no surprise at all, really, that the respiratory rate and the tidal volume and the elastance and the IE ratio and the resistance and the PEEP all contribute to this power which is dissipated in the tissue, particularly sensitive to tidal volume. You see the first mention of tidal volume, the term is squared. So that's a very amplifying power term here. Small changes in tidal volume have a great increase in the power that's dissipated in the lung. Again, that's all well and good, but if you're a marathon runner and if you're a trombone player and if you ventilate healthy people, you can actually put quite a lot of power into their tissue without harming them. So the threshold for what is injurious power and what is safe power isn't clear. And so this becomes less helpful in some ways. So how can we make sense of all this? there's a unifying sort of hypothesis that makes sense of all this if we consider that the lung is heterogeneous. And by that, I mean mechanically heterogeneous, and that the distribution of specific ventilations within the lung is heterogeneous. And by implication, therefore, the distribution of compliances or specific compliances within the lung units follows a sort of a distribution, and it's very heterogeneous. And now this kind of makes some sort of sense. Cressoni wasn't, I'm sure, the first person to talk about this, but it's a well-known paper, and Cressoni has developed a useful way of quantifying it. So that's why I'm highlighting this paper here. The idea of why heterogeneous lung units might predispose to villi is that if you imagine that there's a distribution of neighboring and spatially related lung units with different mechanical properties, then they expand and they collapse differentially, and therefore the shear stresses generated between neighboring units, and it doesn't matter actually whether they're well aerated or badly aerated. What matters is the difference in the gradient, if you like, the heterogeneity gradient between neighboring units. If they expand differentially, then one is dragging on its neighbor and the other one is sort of dragging the opposite way in its neighbor. And this is where inflammation is seen experimentally. And you can image this with fluorine 18 deoxyglucose imaging, or with sort of post hoc in situ hybridization. This paper I'm highlighting here because Cressoni quantifies it quite well using CT scanning. I'm not sure I fully understand this, but this is something that everybody uses, and we have used it too in our lab. You look at a voxel and a high resolution CT, and that's the black square here, and then you create a spherical crust, which is the light gray shell around that sphere. And the dimensions of that are meant to mimic an acinus, about 2.4 millimeters to 3.67 millimeters. And what you're looking for during inflation is the growth in the volume of that crust, the gray crust around the outside, relative to the growth in what was a black voxel. And if they both grow at exactly the same rate, the ratio is 1. And if they grow differentially, then the ratio won't be 1. And that's telling you that neighboring units are all moving at different rates, and that gives you an index of heterogeneity. So now we put this in some sort of context. Volutrauma can be injurious now because even well aerated bits of lung, if they are part of a spectrum of different compliances, will move differentially, and the stress rises. The amplification of stress between these neighboring units is responsible for the mechanical injury. Atelecta trauma makes sense. The atelectatic region, the totally collapsed region, is largely irrelevant, actually. It's not really doing any harm, apart from causing gas exchange to be bad. But in terms of the lung injury, it's minding its own business. And that is not the problem. It's just a marker that we've got a very heterogeneous lung. And if we've got atelectasis, that's one tail of a spectrum, and therefore there must be another tail of the spectrum in the other, and a whole spectrum in between. And it's telling us we've got a very heterogeneous lung. So not surprisingly, therefore, we find inflammatory changes and injury in the non-atelectatic regions elsewhere in the lung because it's very heterogeneous. And when it comes to thinking about mechanical power dissipation, now we can see why some patients suffer and some don't. And this was just highlighted fairly recently by this paper by Pelosi. He tells us that the raw power, the equation that I showed you earlier, is not something we should necessarily take at face value. We need to look at the power intensity. And the power intensity is defined as the power per unit tissue mass available for ventilation. Here's a little sketch of that. Here he In the top graph, you'll see a scenario that's less prone to villi because the aerated bit at the top, the black bit, is large relative to the bottom figure. And so the power is dissipated over a larger space, he calls it, but effectively it's a volume, the volume that is aerated. And that's less prone to injury relative to this bottom cartoon here, where the upper, the black aerated region is smaller, and therefore the power is concentrated in that smaller volume. So that's one aspect of the power consideration. The other aspect of the power consideration, which isn't shown in this graph actually, is the heterogeneity. So we've got one issue is the power per unit volume that's ventilated. And the other aspect is the heterogeneity. Now, if we've got a very heterogeneous lung, the power is concentrated in the regions where the stress risers are, where cheek by jowl are lung units with different mechanical properties. That's where the power is concentrated. So it's concentrated in a small lung, if you've got a small lung, or a small ventilated space, and it's concentrated where those cheek by jowl units with different mechanical properties lie. And he says, I've just sort of taken this quote out of that Pelosi paper, therefore, 1, the total volume to be ventilated, and 2, the inhomogeneous, poorly inflated compartment represent important parameters to be monitored and used for normalization of mechanical power transfer. Those are the two things that we need to monitor. They are two things that we cannot currently monitor at the bedside. Sure, we can measure the aerated volume in a CT scanner, and sure, using the Cressoni technique, we can quantify inhomogeneity in a CT scanner, but we can't really conveniently be taking patients down the corridor to the CT scanner to have a one-off snapshot view and then return them to the ward, by which time everything's changed again. We want really to be able to monitor these two important parameters in real time, all the time, every time we twiddle a knob on the ventilator. And so that's something that my group have been thinking about for a while, and have developed a technique to do that. And the technique actually is not a terribly new technique. It's a sort of an Oxford technique, but it's been around for a while, and it's called the inspired sine wave technique. And the device which we've developed to implement it is, well, we just call it InspiWave at the moment. And you can see on the photograph on the right, the box is bolted to the side of a ventilator. It could be incorporated within a ventilator actually, but this is a sort of bolt-on version of it. And the technique involves injecting a small amount of tracer into the inspired limb of the ventilator tubing. So the patient is getting a small dose of a tracer gas. Now, the interesting feature and the key feature of this technique is that the tracer gas is injected in such a way as it describes a sinusoidal partial pressure waveform. So it oscillates sinusoidally. I'll show you how that works in a minute, but just the little picture on the left is the GUI that comes from the device. And you can see what it tells you, the various parameters we'll come back to later. So how does injecting an oscillatory tracer gas concentration into the ventilator tubing tell you what you need to know? Well, this is the very simple model. Imagine you've got a lung here, that blue triangle, and it's connected to a pulmonary circulation, you'll see underneath, and blood goes round and round, and gas goes in and gas comes out. There you go. Into the inspired gas, we put this signal, this oscillatory signal, this sine wave signal, and that feeds into the lung. And there it is. Now, if you put a sine wave into a big damped inductor, which is what the lung is, not surprisingly, the amplitude of the sine wave gets squashed. And so we can measure the gas on the way out. And if we compare the amplitude of the signal that comes out to the amplitude of the signal that goes in, that tells us about the size of the lung, effectively, or the time constant of the lung. And so there we go. Now, if we use a gas that's a little bit soluble in blood, then some of that signal in the alveolar compartment will get sucked away by the pulmonary blood flow. And therefore, the signal that comes out of the expired gas will have been squashed a bit by the lung volume and a little bit by the pulmonary blood flow as well. So both of those things influence the signal. So in theory, we should be able to infer something about blood flow and about the lung volume and what have you from that. The interesting thing about this technique is that the signal, this oscillatory signal, is flat as a pancake or very heavily attenuated in the mixed venous blood. You'll see the blue arrow here, the big fat blue arrow is the mixed venous blood returning to the heart. So it's heavily attenuated by the body tissues. And given it's only the oscillatory component we're interested in, and that's largely zero in the mixed venous blood, it means we don't have to sample mixed venous blood. So all of those techniques in the past where you had to take a mixed venous blood sample, it's no longer relevant because we're not interested in the mean value. We're just interested in the oscillatory component, the AC component. So the analog, if you want an electrical sort of, thing to compare it with, is a bit like passing an AC current into an inductor. And we know inductors don't like passing AC current. So the current that you get out is smaller than the current you put in. And from that, you can infer something about the inductor you've got in the way. Now you might add some pulmonary blood flow. The pulmonary blood flow is a capacitor that's leaking some current to earth. So the pulmonary blood flow is sucking some of that signal away and sending it to earth. And that's the analogy in electronics terms. But of course, we don't have this in disease. We have a very messed up heterogeneous lung. And so we might complicate that circuit diagram by adding in more components. So we've got an array of inductors and an array of leaks to pulmonary blood flow representing the distribution of ventilation and compliances and the distribution of pulmonary blood flows. So in theory, if we look at the little blue sine wave on the right and compare it to the big blue sine waves on the left, we should be able to infer what the distribution is, but we can't mathematically. It's too complicated. If you have a heterogeneous lung, it's very difficult to make any sense of the nature of it simply by making those measurements. We tried, it's just not possible. So the alternative approach is this. What we do is we create a simulation. And that's what that box is at the bottom. It's like an old-fashioned radio with dials on, sort of, not really, but that's how I imagine it in my head. And so what we can do, we can create any distribution we like in the computer. We can twiddle that knob on the left to alter the mean, so the mean shifts wherever we want. We can twiddle the knob in the middle to make the distribution really fat and very wide distribution, or very narrow and very uniform if we want. And we can twiddle the FRC knob, and we can twiddle the tidal volume and all those things. And we can do what we like. And now what we're going to do is we're going to feed the sine wave, which you'll see this big sine wave, blue sine wave on the left. We're going to feed it into the patient, and we're going to feed a copy of it into the computer, exact same copy into the computer. And then we compare the signal that comes out of the patient on the right with the signal that comes out of the black box on the right also. And then we twiddle those knobs until the patient's output matches the black box output. And there'll be a unique set of parameters where that will be the case. And of course, this is all done in a fraction of a second. And when we've got the signals, the output of the black box matching the output of the patient, we can say, aha, our black box must have exactly the same distribution of ventilations and perfusions as does the patient. And we can simply read it off. And that's what we do. It simplified the mathematics enormously because we just use this simulation technique with Bayesian optimization. And these are the results here. This is actually from a patient here. On the left is a healthy control. And I haven't got a pointer here, but I'll just have to describe it. On the ventilation x-axis, you can see there's a distribution of specific ventilations or specific compliances. They're effectively the same. And on the perfusion axis, you can see there's a distribution there. And in the healthy control, both axes, whether you're looking at it from that direction or from that direction, is a very narrow distribution, because it's effectively a uniform single compartment, single alveolus lung in that healthy patient. On the right-hand side, we see a patient with lung injury. Actually, I think this particular example is from a patient with chronic lung injury with COPD. But anyway, nonetheless, this is an exemplar of how it works. And you can see that the ventilatory distribution is very flat and very fat. And you can see the shadow, the gray shadow that just tells you what that direction of the distribution is. Likewise, the perfusion is quite shallow and quite fat, and this gray shadow shows you how flat and fat that is. So now you can see quite distinctly the differences between this healthy control and this patient with lung disease. So from it, we can measure the volume of lung that's available for ventilation, the EELV, the end expiratory lung volume. Here it is plotted in plot A on the y-axis, and we've manipulated it. This is an experimental animal, a ventilated pig model. So this is the control pre-injury. And as we turn up the PEEP, you can see the open squares tells you that the lung volume increases as PEEP goes up in this particular case. The black dots are a comparator technique, which is SF6 washout. And on the right-hand side, figure B, this is post-injury, the same sort of trend, but the volumes are just down a little bit. So it tracks it, the volume that's available for ventilation, that's available for power dissipation, we can measure. The next thing is heterogeneity, the width, the standard deviation of that distribution, we can measure. And so on the y-axis here is the standard deviation of the distribution of compliances within this ventilated animal model. And in the non-injured, they're all clustered quite close together. In the injured animals, that it's splattered about a bit all over the place. I'm not quite sure why that is, other than that the lung injury that we induce through surfactant depletion is a bit variable. But you can see there's a distinct difference between those two populations. So comparing heterogeneity measured by our technique with that which Cressoni devised through CT scanning is shown here. On the left-hand panel is the heterogeneity according to the CT Cressoni model. You can see we've varied it by incremental and decremental PEEP. So yeah, the open dots and the black dots are those respectively. And in this particular animal, we see that as we turn up the PEEP, the lung becomes less heterogeneous. Moving over to the right, we've done the same thing, but rather than using Cressoni's CT measure of heterogeneity, we've used the inspired sine wave technique, and the blue line is the ventilation, the red is perfusion. Just ignore that for now. The blue line is the ventilation, and you can see there's a similar sort of trend downwards from as PEEP rises, the lung becomes less heterogeneous. I suppose what we should have done is actually plotted one version of heterogeneity versus another version of heterogeneity. I haven't got that plot, but I suppose that would be the logical thing to do. So with this technique, non-invasively and continuously, we get those two important parameters. We can determine what is the volume that's available for ventilation. We ought really to be, well, forget the power equation for a moment, but in very simplistic terms, if we're going to decide what tidal volume is, it's not X mils per kilogram of body weight, it's X mils per mil of available lung to be ventilated. That's the more logical thing to do. Of course, we could then use this information to inform or to adjust ventilatory parameters in that power equation to give us least power or least specific power, least power per unit volume, and also to minimize heterogeneity. Without heterogeneity, nothing really matters. With heterogeneity, all of those stresses that we don't like actually matter and make sense. So knowledge of EELV and heterogeneity allows us to contextualize the concepts of volume trauma, atelected trauma, and power dissipation, makes it make sense. And those EELV and heterogeneity monitoring at the bedside has potential to inform personalized ventilation management in real time to minimize villi. And that's what that's our hypothesis. And that's what we have seen in our animal work. We have a study in ITU patients, not yet started. We have ethics for it, but we haven't begun it yet. But that is the next stage in the journey of assessing these two important parameters that we can now measure. So I think I've done my 30 minutes and more, so I will sign off there. Thank you very much. Shall I keep sharing the screen or shall I come off?
You can come off now, Andrew.
Okay. Thank you very much.
Thank you, Andrew. I'm going to ask someone in the group to lead the questions and answers. Jeff, would you mind leading the Q&A? I'm going to disclose that I'm working with these guys on the commercialization of this technology. So Jeff, if you wouldn't mind kicking us off.
Yeah, hi Andrew, I'm
Hello.
Jeff Shaw. Can you hear me?
I can hear you, Jeff, yeah.
Yeah, it's great. I'm in a little town in New Zealand called Springfield at the moment. It's right in the middle of the South Island in the country. And my internet may not be brilliant. First question is, what's the granularity of the units that you're measuring where you're looking at the heterogeneity as a concept? I'm trying to imagine, are we looking at something about a few centimeters, or we were talking about millimeters or whatever?
Well, when we talk about heterogeneity using this technique, it's a statistical notion. So when you look at a CT scan, you get a spatial dimension, and it's kind of anatomical in a sense. You can see where it is, what it is. You can look at voxel. That's quite different. What we're looking at is a statistical idea. It's not anatomical. You can't say it's in the left lower lobe or, peridiaphragmatic or whatever. And you can't say the neighboring voxel expansion ratio is this, that, and the other. It's simply looking at the distribution of specific compliances, and they're largely, in fact, almost universally, weirdly, distributed according to a log normal distribution. And in health, it's like this, and the log normal distribution, and so we quantify the degree of spread in the standard deviation. So it's very much a statistical thing. It's the standard deviation of that distribution of specific compliances. Now, of course, that in a sense that's meaningless, but it adopts a meaning when it becomes part of the sort of lexicon of medical practice. All sorts of things that we use in medical practice are actually prima facie a bit meaningless. They adopt a meaning because we know what they mean. Creatinine clearance and things like that is all slightly a weird conceptual idea, but we kind of know what it means. And so I think that once we get to understand that, a standard deviation of, 0.1 is perfectly healthy, and a standard deviation of 0.5, actually, you're getting quite fat and bloated now in your distribution, then people will piece together what that means. But, as a statistical term, it kind of doesn't mean anything, does it really? In terms of, spatial physiology.
Right. Is there anyone else that wants to fire a question?
Andrew, does your model, does it allow for the difference between a collapse of an entire lobe or heterogeneity which is spread throughout the lung, like lots of, is there any way to differentiate between, you get a collapse consolidation of one lobe and you get a change in compliance and power, and when you've got small amounts of alveolar, is it able to differentiate between those things?
Well, I mean, if you have a collapse of a lobe, you will see the volume available for ventilation dropping down.
Yep.
Because
Yep.
you've lost it. You may or may not see any heterogeneity change, because
Right.
what you've done is you've just taken a lobe out, and
Yep.
the remainder still has the same distribution. The standard deviation of the remainder may or may not change, because if you simply just have total collapse of a lung, it has zero ventilation, so it doesn't contribute to this log normal distribution. So you will see a drop off in available if you see a sudden drop off in available ventilation, then something peculiar has happened. It on its own, without any compensatory mechanism, it oughtn't to make any difference to heterogeneity. It might be that now you're putting the same tidal volume into a smaller space, and there may be knock-on effects about how that expands it, and it may change heterogeneity in a way, but that'll be a compensatory thing. But atelectasis itself is not heterogeneity, because it's zero.
No. Okay. So but this is, I mean, the problem I see it is that this is where the idea of setting one peak for the entire lung is the problem, because each alveolus probably needs a slightly different peak. And we don't.
That's the problem. We've just got one pipe up here, and we have to use that one pipe to do 2 to the power 23 alveoli. Yeah,
it's a democratic process, and you get the you're trying to find the ideal for a population rather than for each individual.
Andrew, I hate to step in, even though I promised not to. Could you list or tell us the parameters that are on the device? Because I think if the group understood all of the outputs from the technique, they might understand the effect on effective lung volume or alveolar space, and how VDVT is predicted. And then David Dansker,
let me just go back, if I may, and show you where is it? The screenshot of the thing. Sorry, it's being quite slow. There it is. You'll see the GUI here. You'll see that in the dark blue is the ELV, the effective lung volume. Again, that is a slightly conceptual volume, because the whole point of this, there isn't one volume. This is the volume it would be if it was an ideal one volume, but actually this acknowledges the notion that it's actually a heterogeneous space. But if it were a single volume, it would occupy 2.23 liters or whatever that thing is on the top there. So that's telling you what is the available space to put a tidal volume and to dissipate the energy that's associated with ventilation. Then there's dead space beneath that, then pulmonary blood flow beneath that, and then this lung heterogeneity. This version here is not using the standard deviation. It's using a sort of an index. We've played with giving the raw standard deviation, or whether we would give some sort of index relative to what we think normal is. That may change. We haven't quite worked out what unit we're going to describe the heterogeneity in. So that's the sort of readout you get. And you'll see then, if you're changing ventilated parameters, you may see some of these things change, and you can see them trending. The trending screen's not on there. That's just the real time screen going on there, which is CO2 and tracer gas and I think volume or flow. I can't think what the top one is. So that's what you see in real time.
Thank you. I think that was helpful. And then David Dansker had raised his hand. I don't know how to turn that little hand off, but
well, I can turn it off. So I think I should confess initially, of course, that I am working with the group on this development, but it brings back an interesting history to me. You know, when we originally worked with the multiple inert gas technique with John West and Peter Wagner, we did a lot of work using 6 gases and looking at excretion and retention across the lung, and we were able to get some very interesting understanding of the physiology of the normal and diseased lung, but it was a very complicated procedure. So Andrew, you're using a single gas as opposed to the multiple gases that we use that span the solubility from all the way across, from very soluble to very insoluble. How do you see this as, how much sensitivity do you think there is in terms of because we always thought if we could look at the heterogeneity of ventilation and perfusion, we could make changes that would make it better. How do you see this single gas sensitive?
Well, okay, I'm going to just try and, it's a bit mathematical, but I will just do my best here. The reason you have to use 6 gases in midget is to get enough degrees of freedom in a massive simultaneous equation, effectively, and
Right.
Monte Carlo simulation and all that kind of stuff. We use a single gas, so you might say, hold on a minute, there isn't enough information in that. You've only got one simultaneous equation, or just one equation, not even a simultaneous equation. You can't solve it to do it. The reason we get the richness in the data is because we oscillate it at a number of frequencies. If we just do it at one frequency, then we only get 1 degree of freedom. So we can't really, it tells us if we've got one compartment, and if we haven't got one compartment, it gives us a wrong answer. If we have 2 frequencies or 3 frequencies or whatever, actually we probably don't need more than 2 actually, but 3 might be luxurious, then this mathematically gives us the sort of information richness that allows us to solve the multi-compartmentality of the lung. So rather than using multiple gases, we're using multiple frequencies and a single gas. It's much more economical to do.
Get up in the middle of the night to do all those studies I did in the ICU.
Andrew, just following up on that, what are the frequencies that you use, and do you just use 2?
We do just use 2. We could use more, but we found that 2 gives us kind of what we need, and they're not very fast. It's standard sort of, signal processing theory here. I can't remember the name of the law now, but the law is that effectively you're sampling this frequency at the respiratory rate. Every breath gives you an end tidal value. And so there's no point putting in a frequency at a higher frequency than the breath rate, because you'll just get aliasing. Somebody remind me what the signal processing law is that says you can't do it. Nyquist, the Nyquist theorem, isn't it? Yeah. And so the periods are slowish. They can be 30 seconds, 60 seconds, 90 seconds, 2 minutes, 3 minutes. And we kind of choose 60 seconds and 180 seconds because they give enough separation to get rich solutions to the equations. But I mean, if we could be bothered, and if we had the if we had fast enough mass flow controls to inject it, we could put a whole complex sine wave in with bunches of different frequencies. But we're just keeping it fairly simple at the moment to 2 frequencies, a minute and 3 minutes, basically. Quite long periods, really. And people imagine that it's sort of oscillating very rapidly, but it isn't. It's a very slow, sort of pendulous sort of oscillation.
And it takes about 10 minutes or so to get a result?
Yeah, about that. I mean, it constantly updates. If you just leave it running, the sort of the longest period, let's say 3 minutes, will just trundle along, being replaced by another 3 minute period. And so the maths just updates itself. So it kind of updates itself with a sort of lag of about 3 minutes.
Right. Is there anyone else that wants to fire a question? All right, another question. let's say we were.
Jeff, you're getting all the work here.
Oh, that's all right. No, I find this really fascinating, and I appreciated Steve sending out the paper that came out with the mass email, which I read read through and understood probably about 20% of it. But anyway, that's excellent. Now, the question I have is that if we were to apply this technique practically, and we were, say, for example, trying to recruit a patient, with a 10-minute time to get a result, that would mean that a stepwise peak recruitment would take a very, very long time. Have you given some thought as to how we could rapidly get a result with what we can do on a ventilator, which is instant? You know, you can turn the peak to whatever you want instantly, but you don't know whether that's the right thing. When you've got a device that takes a result.
Well, I wonder, when we flip the PEEP, we imagine that something magic has happened the moment our fingers have left the button. I suspect it, the time constant of that avalanche recruitment is in the order of minutes. I think if we'd be hard pushed to have a technology, the speed of the thing we're measuring is about the same order of the speed with which we can measure it, I suspect. We don't suddenly go from bush to bosh when the moment we do the thing. There's a gradual thing. I'm not sure we could really get the time resolution much below 2 minutes. Possibly we could use a 2-minute frequency. But I just wonder whether it would matter, because we're not about creating instant changes. We're about creating slow changes and long-term stability. And what we think are very rapid, interventions actually aren't, I suspect. I don't know, that's my guess, my sense. I don't know.
Yeah, no, I agree. In the intensive care trial with real patients, what will be the clinical question? What exactly will you be looking at?
Well, in animal models, it's quite easy to get nice, elegant designs, and you can test this hypothesis and that hypothesis and do this intervention, that intervention, and look where inflammation, where injury is. In humans, certainly in this early stage, we can't really do that. And I'm not setting myself the task of randomizing people to having this treatment and that treatment and looking for some endpoint, because it's just going to be rather fruitless, I suspect. So what we're going to do is just to be like a spy in the cab. We're just going to be monitoring patients all the time while clinicians do whatever they do, scratching their heads and stroking their beards and twiddling knobs and things. And so we want to know what is, when clinician A scratches his head and twiddles the knob and does this, what actually is happening? What does he think is happening and what is really happening? So we're just looking at this really kind of observational idea of current practice. And then when we've got a better handle on that, and when we're, there are more of these devices out there, then that's the time to do a clinical trial to say, actually, is it making a difference to, people's this, that, and the other, and length of stay and dollars spent and all that kind of stuff. But by and large in ITU, those kind of endpoints are bloody difficult to ever look to ever achieve in smallish trials. So yeah, what we're going to do first of all is just see what happens when people do this, that, and the other. And when some event happens, what do we, what have we logged as the precursor to that event, whatever that event was, whether it's an improvement event, a deterioration event, a change of treatment event, whatever it is.
So in the trial, I understand, will be an observational trial of a whole lot of, whoever comes into the ICU with all sorts of variable lung disease and chronic lung disease as well. It would be fascinating to see what happens during recruitment maneuvers, and also what happens when you prone a patient.
Absolutely, yeah. And the time shift, we know from our COVID experience that you prone a patient and you think, oh, this has not done much good. But actually, nothing happens instantly. The whole gravity takes a while to reorganize the architecture. And so be interesting just to see what that happens, how that affects distributions of pulmonary blood flow, effective volume, power dissipation, heterogeneity, all those things that we're interested in.
One final question, and I've really got to let the other guys have something to ask you. If you were to integrate the power equation into your model, or have you done that yet? So you're looking at
No.
power dissipation? No.
No, we haven't. That's a project for a student, I think, coming up. It's got all the smell of a student project about that. Yeah, you know, it's there are very many versions of that equation, and the problem with it, that a lot of the so-called dependent variables are mutually dependent. So PEEP appears as something that's is a power dissipator, i.e. it increases the power, and therefore it ought to be a bad thing. But of course, PEEP affects elastance, and it may affect elastance in a favorable way, such that the benefit on its effect on elastance is greater than its deleterious effect by just being in the equation as PEEP. So it's a very messy equation because none of those things are independent. They're all mutually dependent. And so it'd be an interesting model to create there, seeing the interdependence of some of those variables, and also what's called the power intensity, the power. So all of that equation divided by ELV. And we'll, and by twiddling PEEP, ELV will change, and elastance might change, and all of those things in that power equation might change. And it's using some sort of optimization subroutine to work out which of those tweaks is going in the right direction and which of those tweaks is going in the wrong direction.
Yeah. Okay. Steve. Oh, sorry, Richard.
All right. Thank you, Dr. Farmery. That was really interesting. Having done midget in the past as well, until IRB figured out what we were doing wasn't really approved in any way, shape, or form. With John Downs when he was at South Florida. I'm a respiratory therapist, so I'm working at the bedside with other respiratory therapists and critical care fellows, and I'm very fascinated, and again, it's really impressive. What's the information that the bedside clinician is going to obtain and say, okay, this has happened to pulmonary blood flow, or this has happened to the lung volume, and how will I translate this into you? I know you don't know yet, really, but what's your thought about how to make this usable?
Yeah.
And I'm just asking that question even related to EIT. EIT is just barely becoming available in the US, and it's much better than initially. I used to tell Steve Blum and Joseph Brunner, who were at SwissDom, every time they show it to me, I feel like they're giving me a Rorschach test, and I'm supposed to know what the blobs are. But again, I'm going on too long, but help me or help us understand, what's your vision for helping people?
Yeah, that's a very good question. I mean, it's going to involve a kind of a model that needs to learn, and there's going to be an AI component to this, I suspect. I mean, some of it's intuitive physiology, but some of these things are so complex and so interrelated that you can't intuit it. You need some help. And I think that's going to come through a clever model through AI. So, for example, if you fiddle with the IE ratio, or you increase the tidal volume, or decrease or alter the PEEP, it may get to the point where it's not entirely predictable what the outcome, what the sort of the adverse influences in the lung might be. Having some sort of modified power equation might be a good way of doing that. So, for example, if you increase the PEEP, then you might reduce heterogeneity, because we've seen that in animal models. But you might also increase the ELV, and that might be good. But you might increase the ELV to the point where the units on the low compliance end of the spectrum are now starting to feel a bit uncomfortable. And what we've found is that when that happens, pulmonary blood flow distribution changes, because all those west zones change and you're slightly strangling those capillaries. So there'll be a whole kind of knock-on And the trick is, or the model's trick is to sort of steer you. Then this amount is okay, but that amount actually starting to impact somewhere else down the line. And so it's tying in all of these things to give you the least injurious. I have some vision of some sort of radial vector diagram with all these parameters like a spider's web, and you have to steer yourself into the bullseye in the middle, somewhere like that. That's the notion I have.
Thank you.
Any further questions from the team? Can I leave you with one final thought, Andrew? When I was a registrar back in the late 80s, early 90s, pulled a paper out written in the Journal of Applied Physiology in 1970 by Jerry Mead.
Yes.
You'll be very familiar with this.
Yes, the condoms.
Yeah. Actually, he had the condoms in the paper. I actually used I printed onto a condom a whole lot of hexagons, and I tried to illustrate the interdependence and the stress and strain that you'd get if you had areas of collapse. It was absolutely fascinating, and I was really intrigued by it all. Can you marry some of the stuff that Jerry talked about in terms of the increased, because it's non-linear. I remember the number was a change in volume, which was a 10-fold from an aerated lung down to a non-aerated lung. And then there was it was the square root of, so I remember a number 4.6, an amplifier that came out of this, so that we had 30 centimeters of transpulmonary pressure, you multiply that by 4.6 and you ended up with 140 or something like that.
That paper is hugely cited, not just because of the comedic condom usage, but because it really was the first sort of popular idea that that stress could be amplified. You know, we naively measure everything at the lips and we imagine that's it. And of course, that's just one conduit in this complex branched structure. And when you've got these mechanically dissimilar things moving into it, that's when the stresses arise. And it was me, oh gosh, what was that, 50 odd years ago, wasn't it? 52, 3 years ago. And so, nothing under the sun is new. We just kind of rediscover stuff, don't we, and reinvent it and reapply it. But yes, it is extraordinary that what we think might be safe, because the dial on the ventilator telling us what the pressure in the trachea is, we're reassured by that, and we shouldn't be reassured by that if there's heterogeneity. If we've got a homogeneous lung, then that's fine. That pressure is pretty much that pressure everywhere. So that's why it's so important to know how heterogeneous it is and how reliable your gauge pressures are.
Yeah, that's been great. Actually, I remember it was 10 to the power of 2/3. So you got 4.6, and
Right.
that was the multiplier. And the 10 came from the change of the volume of the aerated lung versus the non-aerated lung. But I can't remember any more of the maths. Yeah, I better hand this all back to Steve, because I see that we're 1 minute over.
Well, that's actually pretty good, considering the subject matter being so deep. So thank you very much, Jeff. Thank everyone for attending, and thank you, Andrew, for presenting the inspiratory sine wave technique.
Thank you for inviting me.
And of course, it's very promising.